Would you like to try sharing your slides?
Here we go.
Aha, perfect. All right. Well, welcome everyone to the new calendar year. Happy New Year to everyone. This first talk of 2023 will be given by Pamela Fleischmann from University of Kiel. And she's going to speak to us about scattered factor universality, investigating Simon's congruence.
Yeah, exactly. Thanks for the introduction. So especially the talk has two parts. The first part is known by the people who attended the Journée Montoire, so I changed it a little bit and there's something new inside, but it's about M nearly K universality, and later on I have other results. Okay, first, what is a scattered factor? Or has a lot of names, which are sometimes ambiguous, so I use the word scattered factor. And you have a word, and if you delete some of its letters, what remains is a scattered factor. So in the word palindrome, we find the palm, we find an ant, we find a lime, and we find a dome. Okay, formally, if you want to have a scattered factor, U with the letters U of 1 to U of n, then you can put other words, possibly empty, around these U letters, and then U is a scattered factor of V. Tightly related is Simon's congruence. It's a congruence on scattered factors, and what you ask is, do have the two words, the two given words, the same scattered factors of lengths up to 3? So let's have a look. We have the scattered factors AAA, ABA, and BAA in the left word, and we have them also in the right word. The scattered factors of length 2 are in both AB, BA, and AA. No BB in both, it's fine. And since they have the same letters, this is okay. And so they are Simon congruent modulo 3. On the other hand, if we take ABBA and BAAB, then we find the scattered factors of length 3 as, or in the left one, the scattered factor BAA is missing. Since it is in the right one, they are not Simon congruent modulo 3. Or formally, again, I'm looking at both scattered factor sets. I'm looking up to all lengths K, and if they are the same, then they are congruent. The open question, since Simon in the 70s wrote his thesis and then papers about it, is what is the index of this congruence relation? Still an open problem. And motivated by the classical universality problem for languages, we ask ourselves, okay, if I have a W and I have a K, are the scattered factors of lengths K of W exactly all words I can build over sigma of length K? And we call this K universal. So word W is K universal if and only if the scattered factors of length K of W are all words of length K over sigma. This is the same, or is another word for the same thing Karandika and Schnöbelen also introduced. They called it richness. We stayed with universal because richness has other meanings in combinatorics of words. So we renamed it to universality, also motivated by this universality problem. And the largest number K, so I have a word and I'm interested, what is the largest number K, such I find all words of length K as scattered factors, is denoted by iota of W. Okay, so we are well aware that this is only a very small part of the exponentially many cases this we have to look at. So we have to find all words of length k, one is missing, and so on. But at least it's a start. And the general version would be, we call it M nearly k universal if exactly m scattered factors of length k are absent in W. So let's have a look at this word, and I claim that it is 3 universal. And if I write it a little bit more nicely, so I use different colors, and you see in each color bucket here, you find the complete alphabet. You see that you find it 3 times, and since you have 3 buckets, you can pick each letter from each bucket, and you can build all words of length k. This word is nearly 3 universal. Let's do it again with the buckets. And we have 2 color buckets now, and we have a rest here, but DDD is absent. So jumping to this D, and then I don't find a D again, but all other words of length 3 are really scattered factors, because you can take here the all letters you want, and here in this rest are all letters but D, so it is nearly 3 universal. So for abbreviation, call it just nearly 3 universal. This word is nearly 3 universal. So the question is, why is this the only one? Okay. A very important tool in investigating scattered factors and the universality especially is the arch factorization introduced by Ibrahim. Given a word, and you take the alphabet, and now you go through it. We see an A, we see a B, A, C. Now I have seen all letters, and I close my first color bucket, or my first arch. Now I'm doing the same, and I've seen all of them, and I'm doing it again, and here in the rest, I don't find it. So we have 3 arches, and we have a rest, abbreviated by R of W, it is BC. 3 arches, so iota of W is 3. And another important thing is the modus. The modus of a word is the word containing the unique last letters. So all these letters here at the end of an arch are unique because we closed the bucket when we saw the complete alphabet. And this is the modus. Why is the modus so important for investigating scattered factors and absent scattered factors? Because the modus is nearly the only information where you exactly know, if you have a scattered factor, where you are. So if I say my scattered factor starts with a C, then I know this position is the first position my scattered factor can start. If I say the next one has to be an A, then I know immediately I'm at least here. This is the reason why the arch factorization and the modus are so important. Okay, so the first characterization, which is now pretty old, is a word is k universal if I have at least k arches. And this is also the same Karanika and Schnübelen also derived. And all words with more than k arches are in one congruence class, because they all have they are all universal. They all have the complete set of words as scattered factor set. Now let's have a look at the words where exactly one scattered factor is missing. The first question is, so we can't have k arches because then none is missing. So the question is, can we have k minus 2 or less arches? Okay, let's take an example. I have 5 arches, and I say in the rest I don't have a B. But I know that I have only k minus 2 arches. So I'm looking at scattered factors of length 7 here. But what I can do is I'm jumping this modus. Then I'm taking the B here. And then I can add A1 and A2 if the alphabet is large enough, so I need at least 2 different letters, I can add A1 and A2, and 2 scattered factors are missing, which means if I have K minus 2 arches and at least 2 different letters, then it cannot be nearly K universal. So we know nearly K universal words have K minus 1 arches. Next thing which we had in the arch factorization is a rest. Is it possible? So we need a rest, otherwise we would be K minus 1 universal. So the question is it possible to have 2 or more missing letters in the rest? Okay, let's do it again. Now we have 5 arches, and we know that we need a scattered factor of length 6. But in my rest, I don't have an A and a B. So what happens is the same. I'm jumping the modus, and I add the A and the B, and both are not scattered factors of length 6. So this is neither working. Okay, so we know nearly K universal words have exactly 1 missing letter in the rest. The question is, do we have a characterization by now? So can I say we have a W is nearly K universal if and only if I have K minus 1 arches, and the cardinality of the rest alphabet is the cardinality of sigma minus 1. Let's look at this example. So I have 3 arches, and in my rest, I have a C missing, so everything is fine. But unfortunately, ABAC is missing, so jumping the modus, but also AAC is missing. So I'm not jumping to the modus here, but I'm taking something from the inner of the arch, and it is missing too. So we don't have a characterization yet. The characterization needs the constraint for the rest for all middle rests. You will shortly see what I mean with this. Here, I'm building the arch factorization from the right, and I have a BC here. And we notice A is missing. That's great. Now I'm building in blue the arch factorization from the left, and in green still the arch factorization from the right. And there is a middle part. And this middle part has exactly 1 letter missing. It's a B. Now I'm moving 1 arch more from the left, means 1 arch less from the right, and the middle part, again, 1 letter missing. And I'm doing this, I'm moving these arches from left to the right through the word, and if in all steps, exactly 1 letter is missing in this middle rest, then I have the characterization for nearly K universality. So the word's nearly K universal if I have K minus 1 arches, and this is a formal way of writing this part from left and right. So U is a perfect universal word, meaning I have no rest, and we call it perfect universal, and I'm coming from the left. V is a perfect universal word, and since it's here reversed, I'm coming from the right, and I have this middle part here. And this middle part misses exactly 1 letter from the alphabet. And since I'm doing it for all U and V, I'm moving U, so the length of U, the number of arches, through the complete word. Okay, so we now have a characterization for nearly K universality. This means that each word in sigma to the K determines a congruence class with respect to Simon's congruence. Let's consider the word U with A, B, C, C, A, B. It has length 6. So if this one has to be absent, I know that I have 5 arches and I have a rest. So I'm drawing this, and now I can construct the word where U is exactly missing. I'm writing U's first letter as a modus of the first forward arch. Then the second letter, the third letter, I will explain the boxes right away. The fourth letter, the fifth letter, and I know there is no B. because now I know jumping here through the modus, I don't find a B here. Now I'm doing this backward thing. B, A, C here is the same, C and B. So now I have to fulfill that these are arches. So for this, that this is an arch here. Wait, I have no A here in this part, missed this. I need here a BC, but this part here, the small part, we said, okay, only one letter missing. So I can't just put a C here. I have to put the CB or BC here. Now for the next, the modus is a B, so I have to put AC here, then AB again, BC, and there the AC. And voila, we have a word where exactly U is missing. And this is a short lex normal form because we ordered them here. It's the shortest form by the characterization we had. And since we assume an ordering on our alphabet, this is the shortest word and the lexicographically smallest. We can speed this a little bit up. So since I know that this B here is the last modus of the backward arch, I can just look at both at the same time and put a BA here. So, and I'm doing, and then I fill the arches immediately. So this, then I get it a little bit faster, not with going twice over the word, but with once. Okay, so so far so good. The next question was, what is about 2 nearly, 3 nearly, or for an arbitrary M? And for this, based on work from Florin and his group, we had a look at their algorithm and found a characterization of their idea. And this led to the so-called, or we called, alpha beta factorization. If you have such a word with a forward and backward arches, the part where both arches have their modus is called beta I, and the part without the modus in between is called alpha I. This means that in the complete word, we know the beginning of beta I because it's a backward modus part. And we know the end of each beta because it's a modus letter from the forward arch factorization. And the alpha E are then just for filling up the arches. And you can put them inside arbitrarily often and permuted. For 2 nearly K universality, we have still a nice result. So what do we have? Again, it's nice. We again have K minus 1 arches. But now it may be that one alpha J is missing 2 letters, or and the rest. So no, sorry. We know exactly one alpha I is missing 2 letters, and all other alpha J are missing exactly 1 letter. Then you have 2 nearly K universal word. Here we have so many congruence classes. So K times the cardinality of sigma over 2, and then the alphabet to the K minus 1, different classes. With 3 nearly, it's getting ugly. So first of all, let's take a unary word. In this unary word, A, B, B, A, and B, B are obviously absent if my alphabet is A and B. So here, if our M is at least 3, we first get that we don't have any more that the number of arches as Yoda of V is W is K minus 1. It may be that we have less arches. And we have a characterization for this one. So either W starts, so we have only 2 letters, A and B, and W starts with one of them twice, and then the same again. So as you saw in the a word there. Or if you have more, then you have again the k-1 arches, and you find one arch where 3 letters are missing, and all other alpha j's, so all other parts have again, so all other rests have again 1 letter missing. Or you find 2 adjacent of these alpha I, so alpha I and alpha I plus 1, where exactly 2 are missing. And the concatenation of these possible missing things is not a factor of the beta in between. It's getting ugly, but I will tell you how it works. Here's again the alpha beta factorization. And here we have an alpha A, an alpha where A and B is missing. And here we have an alpha where B and C is missing. So absent is, I'm jumping to the C, and I'm jumping to C, D from the right. Now I'm here in this middle part, and I'm filling it up with a CB, because here is no C, here is no B. The C from left, the CD from right again, and I'm filling it up with a DC. I will not find a DC. CA, I'm sorry, I'm here in CA. And we have the BB. Since I said that one of them here is in the middle, I ensure that the fourth one, which is BA, I will find it here. So since I make sure that, so I have 4 possibilities, 3 of them I exclude, the 4th one is in the middle beta. This ensures that exactly 3 scattered factors are missing. Okay, Manon, you have to pay attention. From now on, it's new for you.
Okay, I'm here.
Okay, so we don't have more. We don't have more results so far. No, we have them, but they are unpublished, and we are working on them for Words and DLT. So hopefully you will see them soon. But we have no characterization so far for higher M. But I brought some other parts with repetitions. We also started this research with the first paper we published about universality, scattered factor universality. And we looked how is this, the universality changing if I repeat a word from which I know it's k-universal. And the first result from this is that a word is k-universal if and only if the scattered factor set of length k does not change if I repeat W twice. So why is this? So the one direction is clear. If I already have all scattered factors of length k and W, then I will find them in W squared. For the other directions, if W has more than k half arches, well, then I can find k half in the first one and k half in the second one, and I have k in total. If I suppose that I have strictly less than k half arches in W, then I'm taking my modus. I am taking the letter which is not not in the rest. I'm taking the modus again, and I will not have a scattered factor. And I can do the same by just putting them together. So I have missing scattered factors, and they would be both in W squared, but they are not in W, which means this set is not the same. Okay, so we know k universality is equivalent to the scattered factor set of W is the same as the scattered factor set of W squared with length k. So we are always referring to a fixed length k. By this, if I repeat W n times, I have at least k n arches. But sometimes funny things happen. So if the rest here which is not in the arch, but I can combine it with the beginning of the next word, and I don't need the next letter, the first letter or some first letters of the word for the arch, and then I get an additional arch. So the question is, when do I get an additional arch? Do I always get an additional arch? And for this, we introduced circular K-universality. And a word is called circular K-universal if a conjugate of W is K-universal. I have an example. This one is not 3 universal since DDA is missing. So again, this is a modus and this is a rest. So DD and A obviously missing. But it is 2 universal. And if I move the first A to the very end of the word, which is a conjugate, then I'm 3 universal. So if we go back here, the modus was a D. So it is allowed that the modus changes. It's allowed that I move the arches to the right, but in the end, I get an additional arch. So a conjugate is 3 universal. So we are circular 3 universal. Now, we wanted to know, okay, when exactly does this happen? And we parameterized the iota function and said, okay, iota W of S is nothing but iota of W to the S. It's the same with the circular universality. And then we were able to define the nabla of this function as the gross of the universality with respect to the powers. So just putting one W more into my consideration, and I'm looking, okay, how does it change? And this is nabla. And we have, if the circular universality is one bigger than the normal universality, then I will always get an additional arch. So this means here we repeated W S times. So I have for sure this S times W of iota of W. And this here are all parts where 2 copies of W meet. And in all these meeting points, you get an additional arch. You have this if the circular universality is one bigger than the universality. In the binary alphabet, we always also have, or we can say that this is the otherwise case. So if it's not, then you never get one, but it only holds in the binary case. Let's have a look. Here we have 2 arches, and also the circular universality is 2. And if you double it, you get a 5, so you get an additional arch in between. But if you put W 3 times, or you take W 3 times, then you only get 3K plus 1. So from W to W squared, you get an additional arch. From W squared to W cubed, not. Okay. Question, when is nabla K and when is nabla K plus 1? And this has again something to do with the rest, with the arch factorizations from both sides. So arch factorization from the left to here, C is the rest. Arch factorization from the right ends here, and here you find a prefix which matches the rest. So iota of W squared is iota of W plus iota of P to the minus 1 of W, so cutting this off. And P is the longest prefix such that the universality of the word is not changing. The first thing is, if you look at the universality of the concatenation of 2 words, it is exactly 1 larger than the universality of both if the rest of W with a reverse, so now looking for right, to left if they both give the complete alphabet. You see this also here. So if you now look at W square, arch factorization from the right, arch factorization from the left, and if you have in the middle a complete sigma, then you get the +1. So the nabla function, the nabla of iota W, and the function which maps S to the rest, only the rest of W to the S, they depend on each other. Where we are always looking at the rest. And what we are doing here is saying, okay, if I have a W to the S, I'm taking the last occurrence of W, and now I want to know what is the rest of this one. And we notice that I can build, so the rest of W to the S is obviously the rest of the rest by forms of this one. And so we can compare the alphabets. And if I have that, if the alphabet of U and the alphabet of V are the same, but a strict subset of sigma, then I can put them in front of U's and the rest remains the same. If I'm doing this with the rest of W to the S and W to the T, then I'm getting that I can add more W's to both, so W to the S and W to the T, and the rest is the same. The converse is not true. So if I have this one, I cannot just go down on the same amount of both. But I can do it somehow. The alphabets remain the same. So not the rest themselves, but the alphabets. This means that the growth of the universality index is eventually periodic. I have to find the smallest part from which on I can add something, and the alphabets of the rest are the same. And I can stop before the cardinality of sigma, because afterwards, so it will not do anything new. So we have theorem that I find, or there exists S and T both smaller than the cardinality, and the loss of generality S is smaller than T, such that the rests are the same, and the alphabets of the rests are the same. And the growth is the same. Okay, beginning at S+1, nabla has a period T minus S. So far, we investigated W to the S and said, okay, this is the same, as we all know, as W to the S minus 1 concatenated with W. And for us, it was completely astonishing that if we take the first W out and have a look at the same, so again, looking at the rest and so on, it makes a difference. So if the rests of W to the S and W to the S+1 are not the same, then the gross is exactly iota of W, so I get only my K arches, what I always get, if and only if the rest here is a suffix from 1W more. And I get an additional arch if it's the other way around. This gives us a following corollary. If the alphabets of the rest of these two consecutive repetitions are not the same, then I have that the gross is the normal iota, the normal K, if the alphabet is strictly included in the alphabet of the rest of W to the S+1, and I get the additional arch if it's the other way around. So the question is, when is this function in this time eventually constant? So, which means when is a corollary applicable? And we were able to show that it is eventually constant if and only if nabla is eventually constant. So we can look at the one which fits better. But this also means that if the circular universality is one larger than the normal universality, then this function is eventually constant. So if I have the nabla and it is k on an interval to n, then I know that the alphabet of the rest of all these repetitions of w are included in each other. And we have an equivalence when the chain is strict. So if we have an implication here, and if we can find if we are here and then the subsets are strict, then we can also get that we only have always k additional arches. So we have ascending chains, and this ascending chains imply that the alphabet, the cardinality of the alphabet of the rest is s minus l for all s in this interval, starting from l and going to l plus cardinality of sigma minus 1. But we know that strictly ascending chains of length cardinality of sigma plus 1 cannot exist. I only have sigma letters, and I have the rest, and the rest is defined as there is at least one letter missing. So what we have is that the gross is iota. If the gross is iota, then it is iota everywhere. So if it's iota in this interval to the cardinality of sigma, then it's everywhere iota of w. And this means that we have an equivalence between the gross is only this iota, and the gross of the circular universality is also iota of the smaller alphabet, on the smaller interval. So what can we say? If the circular universality is a universality plus 1, then I always get an additional arch. And if the gross of the circular universality is iota, then iota of w to the s is s. So each w brings its own k arches, but I don't get any more. But I can also have descending chains, as we saw. And if I have a descending chain of the rest of bits, then I know that the cardinality of this one here is.
Hello. Is it is your internet okay now?
I hope so. So the question is, where do I have to restart, or what should?
Yeah, I think we're losing the connection again.
Zoom is telling me I don't know if it makes any sense to proceed. I'm sorry.
Okay, right now it seems okay. I can see you, I can hear you for the moment. Oh no, maybe not. Okay, yeah, it seems like,
I think.
Yeah, I think the connection is not good. Maybe we should yeah, maybe it doesn't make sense to to keep going.
Yeah, exactly. I'm really, really sorry.
Oh, that's okay. No, I think
So there wouldn't have been much. So what in the end we can say, okay, we can compute it in constant time, and we have some pre-processing. We can compute the circular universality, and from this we can compute if we have this additional arch or not. These are all my co-authors over the many years, and thanks for your attention and your patience with my internet.
Oh, that's right. Thank you very much, Pamela. I'm sorry you